This video goes over step 5 where we determine the hydrostatic stiffness. Now, you only need to do this, as I mentioned in the previous video, if you're going to use the full definition of hydrostatic stiffness that presented in an earlier video. If you're just going to use the approximation, the single term, which a number of people do, if you're just going to use that, then you do not need to do this step. That will be done by the program later. Also, if you are importing the mode shapes, the nodal displacements, and so forth from another structural analysis program, then you don't have much choice, unless that program also calculates the hydrostatic stiffness. You don't have much choice other than to use that formulation that uses just the single term. So you wouldn't need to go through this step either. Now this step is admittedly rather complex, and so I'm going to go over the input file to explain things to you. So the input file is kf.txt. So if we open that up, we'll look at this a little bit. So first I define some parameters here. So I define gravity, and you can look at the help for this definition of the definition that's required for the gravitational acceleration vector. So, but 0, 0, minus 9.1 says that gravity is in the negative z direction and the magnitude is 9.81. I define a tolerance here, which we'll talk about in a bit, as well as a number of iterations, the maximum number of iterations, because we're going to need to do an iterative solution. And I also define the weight density of the water. So we need to input, this whole process involves a static analysis of the structure in water, calm water. So we need to redefine the structural mesh. And so if we look at this file here, it's the same file that we had before for the eigenvalue analysis, except for a few changes. And really the only change is down here at the element level, and we need to do a couple of things. We need to tell it to use external pressure, and we need to tell it to form the geometric stiffness, the hydrostatic stiffness matrix for the element. Without these parameters, then it's not going to get the pressure and be able to solve or calculate the hydrostatic stiffness. The other change is right here, local equals 1. So normally the default for this element is to calculate the stresses in a quadrilateral coordinate system, but to calculate the hydrostatic stiffness, we need to have it calculate the stresses in a local triangular coordinate system. So for each triangle sub-element of the quad, that needs to calculate the stresses within that triangular coordinate system. So that's what local equals 1 means. And that's the only change in this file as compared to the previous mesh file, the FEA mesh.txt file. So let's go back to kf.txt. So we file that in. The next step is to define boundary conditions. So this structure is floating in water, so there are 3 rigid body modes: surge, sway, and yaw. Heave has hydrostatic stiffness, roll and pitch have hydrostatic stiffness, so they're not rigid body modes when the structure is floating in water. So we need to restrain those modes. We need to impose 3 constraints. There's 3 modes to restrain, so we need to impose 3 restraints on the nodes to restrain those nodes. So we choose to restrain this particular node, and there's some flexibility here in what you choose. So we restrain this node in the x direction, so that that restrains surge. We restrain it in the y direction, so that restrains y. And we need to restrain another node, and depending on where it's located, we could either restrain it in the x or y direction. There's some conditions where it has to be one or the other. But in this case, we restrain it in the y direction, and that restrains yaw. All right, so then we need to define the pressures acting on the nodes. So the hydrostatic pressures acting on the nodes. So the command nodal pressure will do that. N equals all means do it for all the nodes. Pattern is just tells it to apply those pressures for the load pattern 1. Dash hydro says calculate the hydrostatic stiffness. To understand all of this command, just look at the help for nodal pressure. Density says to use the weight density. We need to calculate the weight density. And then no negative means do not allow a negative pressure. So that means any node above the still water line will have no pressure applied to it. And then node order, that's the same as before. We want to optimize the node ordering for equation numbering. And then we set a, we need to do an iteration. So this process requires the initial estimate for the location of the structure to be close to its equilibrium configuration. This is not a large displacement analysis where we can have the structures sink substantially. This is just a sequence of linear analyses, and so linearity is a restriction, which means small displacements, which means we need to start off with a pretty good estimate of the actual position of the structure in calm water. And we're going to go through and calculate the displacements in an iterative process. And what's changing is, of course, the hydrostatic stiffness depends on the geometric stiffness of the structure, and that's the stresses in the structure in calm water. And so that's unknown, so we need to calculate that, and it's an iterative process. And so what we're going to do is we're going to do a sequence of analyses refining on the stresses, and the convergence will be when the displacements, the change in displacement is sufficiently small. So we set up a displacement norm here, just a value here, which is going to be larger to keep us moving. So this is the loop here, do down to here to do. So this, if you're familiar with do or for, some languages use for, this uses do. So we go up to a maximum of number kf iterations. We form the stiffness, we convert it to sparse storage for efficiency. We solve for the displacements. State is a new command for us. That solves for the stresses in the members given the displacements calculated by LSolve. And then as long as we have to do a minimum of 2 iterations. So if the number of iterations is more than, if the iteration number is more than 1, we look at the difference in the displacements between the two iterations. And if it's if the maximum is less than our tolerance, that's where our tolerance comes into play. If the maximum is less than our tolerance, then we break, we stop the iteration. So here that just prints the iteration number, a number of iterations is required, and here we print the maximum difference in the displacement that we calculate. PDISP will print all the nodal displacements. Could be large again. You may want to do that and may not want to do it. However, you should check it to make sure that they're not ridiculously large. So if you haven't, if the structure is not in equilibrium, in other words, if weight is not equal to the buoyancy, then you're going to get large displacements until it tries to capture that. Or if the structure is not very well designed, then there could be some large flexible motion, and that could result in unrealistically large displacements. So you should look at the displacements and see how they are. Make sure there's not something wrong. If convergence wasn't met, then this just returns because there's no point in continuing. P state will print the states, the stresses for each element under the gravity loads. So that includes the self-weight of the structure and the hydrostatic pressure. So the next step is to calculate the hydrostatic stiffness. What we've done up here so far is we've calculated those stresses. Now we need to do that. Now we need to use those to calculate the hydrostatic stiffness. So we've already calculated and included in our analysis the elastic stiffness, the stiffness that depends upon Young's modulus and shear modulus and so forth. And that's captured in our eigenvalues. So now we only want to calculate the stiffness from the hydrostatic stiffness, not including the elastic stiffness. So the approach we're going to take here is we're going to define a new mesh with small values of Poisson's ratio, with small values of Young's modulus and shear modulus, so that that elastic stiffness is essentially zero. And then what's left then in the formulation will be the hydrostatic stiffness. So to do that, we first want to copy the stresses, and they're kept in .min5s underscore st. This is true for any element. So if you're using an element besides min5s, or in addition to min5s, you would want to do the same thing. You want to save those stresses to be able to have access to them later. Because when we redefine the elements with these new material properties, it's going to delete the array that contains the stresses. So we're going to so the stresses are put in .min5s underscore st, and this is standard. So it's always a dot. It's going to be the element name underscore and then st. And we're just going to move that into, or copy that into, actually we're moving it into min5s st. So let's look at this file here, FEA mesh-kf only. So I've already opened that. And the only difference between this and the other mesh file that we just used is that I am now using some very small numbers for Young's modulus and for the shear modulus, so that we don't get any elastic stiffness. We only get the hydrostatic stiffness. So that's the only change. So we come back here. So we file this in. So this new mesh, if you will, is defined. And now we want to move back those stresses that we saved into the appropriate named array, so that when the element forms the stiffness, it's going to have access to those stresses that we calculated in calm water. Also, we want to now remove the boundary conditions so that this thing is freely floating, so that there's no restraints on them. We need to redo the node ordering because of the change in the boundary conditions. Actually, normally you may not need to do that, but there's no harm in doing it. I recommend doing it. This just prints the element information, which is optional. Form K, and here we're just forming the stiffness. We don't need to do anything other than form the stiffness. So I added the qualifier -diff. So here you remember that we saved the 18 modes into a file, eigen underscore post.phi, and so I'm reading that file into a matrix phi, and I'm doing I need to do phi transpose k phi to get the modal hydrostatic stiffness, the kf star from our equation of motion. So this, if you'll recall, that's phi transpose kf phi. So I'm pre-multiplying, or I am multiplying .kstr times phi. The p stands for profile multiply because .kstr is in profile form. So I'm multiplying kf times phi, and then I'm transpose multiply a phi times that temporary result and into the matrix KF. And then here I just print the KF matrix, which is going to be an 18 by 18 in this particular case, because we said we were using 18 modes. And then I write that a matrix to a file for later use. And then I return. So let's see how this works in practice. It's going to be relatively quick, but it does involve iteration, so it does take some time. So again, we have now 3 here, but not what we want. We want KF. So I'm going to say KF, and then just file it in. So now it's doing the iteration. So it's done. So let's quit this. So let me just quit it here, and we'll go to kf.out and open that up. So this is the kf.out file. If we scroll down here, we see that it required 3 iterations. The maximum displacement change between iteration 2 and iteration 3 is less than our tolerance level. And so then if we look at the displacements, we see that the z displacements are larger than the other 2 displacements, which is what we would anticipate for especially for this structure, and the fact that it's trying to find an equilibrium position to balance the weight of the structure, which is now distributed. It's not like it's a rigid body analysis, so which is distributed, the weight of the structure with the hydrostatic pressure. So we can now proceed to, if we jump all the way down to the end of the file, we have our 18 by 18 hydrostatic stiffness matrix. And we notice that surge is small, like it should be. Sway is pretty small. We should check that, make sure that this is reasonable estimate for the rigid body heave stiffness, and it is if we were to do the calculation. We should check that this is close to the rigid body roll hydrostatic stiffness, and that this is close to the rigid body pitch hydrostatic stiffness. This is the rigid body hydrostatic yaw stiffness. It should be 0, but we notice that it's not. If we look at the magnitude of this relative to this, it's pretty small, relatively small, right? 10 to the 6th power different. And my observation is that to get this to be 0 requires a lot of cancellation between all the different elements coming together to form the structure, and that we oftentimes don't get the 0 here. And there's actually another reason for that has to do with the particular shell element that's being used in the program right now. But it should be pretty small. And then this is the hydrostatic stiffness diagonal associated with mode 7, which is the, if you recall, is the first vertical bending mode. This is the second vertical bending mode. This is the horizontal bending mode, and we see that that's quite small value. I need to point out something here. If you'll recall, we replaced the mass normalized rigid body modes with the non-mass normalized modes. In other words, we replaced the mass normalized surge with just a unit surge and so forth. So the magnitudes of the displacements of these modes are going to be substantially larger than the displacements in the deformational mode. And that's why the values for the rigid body modes are so much larger than some of these other values for the deformational modes. It's because the displacements in the deformational modes are much smaller than the other displacements. And so because we're doing phi transpose k phi, that becomes squared, and so there's a huge scale factor here. It doesn't affect the results. The results will come out correctly, but it would be incorrect to compare this value with a non-scaled mode, if you will, to this value with a scaled mode. One would need to scale, say, this heave stiffness to reflect the different scaling of the modes. All right, so that does it for this video.